Welcome everyone back to 264A Automated Reasoning, and today we will be talking about a new circuit type which is known as Sentential Decision Diagrams, or SDDs. This is an influential generalization of OBDDs. It's actually one of the latest circuit types compared to the ones we looked at. It was about less than 10 years ago, and it's been influential in a number of applications. We'll see later, particularly when learning from data and knowledge, a combination of data and knowledge. So we will discuss it first, and then we will move on to the subject of bottom-up compilation. Remember, we mentioned two ways of compiling: top-down and bottom-up. We talked about top-down, and today we will talk about bottom-up because that actually is applicable for both OBDDs and SDDs, and we will see why. So let's go ahead and move to the whiteboard and get started with our discussion. All right, so we'll be talking about sentential decision diagrams, also known as SDD circuits. And since they are a generalization of OBDDs, we will actually start by a quick review of OBDDs so that we can motivate and see in what way they generalize them. You see an OBDD here over 4 variables. And as you remember, we have actually a variable order ABCD, which is required for an OBDD. And if you give me a variable instantiation, let's say A is false, B is false, C is true, and D is true, then you go ahead and find out whether that particular variable instantiation is represented by the OBDD. And that happens when you follow the paths from the root, depending on the variable instantiation, then you reach a 1. So if you recall, the dotted lines represent low children. We follow these when the variable is false. The high childs are those that are solid, and we follow these when the variable is true. So in this particular case, we have A false, we go down here, and then we have C true, we go this way, and then D true, we go that way, and we reach a 1. And that basically tells us that this is a particular instantiation that satisfies this OBDD. And if we reach a 0, that means it doesn't satisfy the OBDD, and that characterizes the Boolean formula that is represented by that OBDD. Now, as we mentioned before, you need a variable order for this, and we mentioned that OBDDs are unique once you fix the variable order, if you make sure also that the OBDD is reduced, and this is what we called canonicity. It's something that is important, and we'll see why later. We mentioned this briefly, but you'll see there are other reasons for why canonicity is important. And as we discussed in our last lecture on OBDDs, the variable order does matter. We've seen a situation where the size of the OBDD can be linear in the number of variables versus exponential in the number of variables, depending on which particular variable order you use. Now, we will look at, again, what makes OBDDs particularly important and why for a while people actually wanted to generalize them. So as mentioned earlier, they've been heavily studied. There is a lot of literature on OBDDs, and some refer to them as the most studied tractable representation of Boolean functions. So we mentioned canonicity. The fact that you have a polytime apply, remember what apply is. Apply takes two OBDDs and combine them using a Boolean operator like conjoin or disjoin. And the fact that you can do that in polytime, in particular quadratic time, has all kinds of implications. You'll see later when we talk about compilation and bottom-up compilation, you'll see that apply is at the heart of doing bottom-up compilation. OBDDs have been very popular in certain areas of computer science, like formal verification, where they're used to represent states and manipulate them. Depending on time, we may talk about this application later. And they've been also supported by some really very well-optimized software systems that are available publicly. CUD or CUDD is actually a very famous package, probably the #1 package for doing OBDDs. And the other thing is, and you'll see later, it's very critical when working with OBDDs to have good variable orders, which is a subject that have been studied extensively in the literature. You'll find a large number of ways of coming up with good variable orders in packages like CUD and so on. So a very versatile representation of Boolean functions that have been very well researched and investigated. And people wanted to generalize OBDDs to come up with something that tends to be smaller in size, but maintain as many of these properties as you can. And that quest has been going on for decades, actually. And remember, in our knowledge compilation map that we discussed a while back, we found that OBDDs, even though they give you the most power in terms of what you can do in Polytime, they also tend to be the least succinct. So they're large compared to other things like DNNF and deterministic DNF. So the question is, how much of this can I preserve while coming up with a circuit type that tend to be smaller, so I'm able to scale further? And Sentential Decision Diagrams was basically, in a sense, the latest way of doing this, and I would say perhaps the most successful generalization of OBDDs. And we'll see why sentential in comparison to binary in just a little bit. But I introduced these in 2011, so less than 10 years ago. And let's see how they work. And for that, we want to talk about notation a little bit. So this is how OBDDs are typically notated, as we see here, as decision graphs. And we're going to adopt this notation for them. And you'll see why we're doing this in just a second. But the idea is that I'm going to translate each one of these decision nodes into something that looks like this. Think of this as an OR node, and this is as an AND node. So this would be an OR, and this would be an AND. We've done this before. So if this is alpha and this is beta, in the past we went ahead and said, let's do this as OR, and in this case I have A and alpha, and in this case I have not A and beta, right? So it's basically the same thing, just a different notation, and you'd see why we're doing this. So you can think of OBDDs as representing this, right? And we'll call this again a decision node, and it has two children. And the reason we're doing it this way, because in SDDs, we'll have something similar, except that a decision node would look like this now. So what's going on here? This is still the OR node, and each one of these guys is still an AND, except now, instead of just two of them, I can have an arbitrary number. And if you look back here, every OR node had two children. And if you look at this here, it was a variable, and this was the negation of the variable. The decision nodes in OBDD, in SDDs, not only will you have multiple ones, but these P1, P2, P3 will actually be arbitrary sentences. So they're not just literals. They're not just a variable and its negation. And if you, again, go back to the OBDD picture, we will say here, this OR node is branching on a variable A. So if A is true, it goes this way. If A is false, it goes that way. In SDDs, we will say that we're branching on sentences. In this case, P1, P2, P3, and there could be more. And the requirement here is that these P1, P2, P3 are mutually exclusive and exhaustive, and they cannot be false. So precisely one of them will be true, right? Two of them cannot be true at the same time. And we'll see a concrete example in just a little bit. And as far as notation, we do call these P1, P2, and P3, we call them primes. And we call the S1, S2, and S3 subs. So a decision node is made of a number of prime sub pairs. And again, the intuition is that primes are mutually exclusive and exhaustive. And depending on which one of them is true, then I pick up the corresponding sub. And you can see how this generalizes what happens in OBDDs, because in OBDDs, we have exactly the same picture, except we only have two primes always. Let's say X and not X, right? That's it. We only have two primes. A variable and its negation, but in this case, we have arbitrary sentences. Now, that's the primitive from which SDDs are made of. And we'll see that primes and sub are themselves represented as SDDs. And let's take a concrete example next to see how it looks. All right, so this is a fully fleshed out sentential decision diagram, or an SDD. And you can see that I have 1, 2, 3, 4 decision nodes in this particular case. It looks weird as far as notation, but you know how to interpret that. Again, this is an OR, and this and that, this and that, and so on. And just like OBDDs require a variable order, we're going to see that SDDs require a Vtree, like what we're seeing here. So basically, every SDD has to conform to a Vtree, and we'll see that in a precise sense later. I just wanted to give you a quick overview before we dig into the details here. So the two generalizations so far is that we have these general decision nodes that branch on sentences instead of variables, and then we have to adhere to a Vtree. A Vtree is simply a binary tree where the leaves correspond to variables. You could have any of them. And what we will see is that if you build an SDD with respect to a special type of Vtree that we call a right linear Vtree, then what you'll do is you'll get an OBDD as a result. So OBDDs are a special case of SDDs when I insist on using a right linear Vtree. And again, you will see this in a little bit in more detail. Now, what is a right linear Vtree? A right linear Vtree is one in which every internal node, the right child is a leaf. So here's one internal node, here's another, and here's another internal node, and here's another internal node. Look at this guy. The left child is a leaf, left child is a leaf, left child is a leaf. So you can think of this as like a variable order A, B, C, D. If you build an SDD with respect to one of these, as I mentioned, it ends up looking like this, which is effectively an OBDD. All right, and that's the way in which SDDs end up generalizing OBDDs. We're going to say more about all of this in just a little bit, but I just wanted you to see the big picture of what's going on here. All right. Now, here's the summary before we move on and what makes SDDs interesting. So as we mentioned, it's a strict subset of OBDDs characterized by trees instead of variable orders. We branch on sentences instead of variables. They do maintain the key properties of OBDDs in the sense that they're canonical. They have a polytime apply operation. There is a star here. We'll explain that later. And the main thing here is that SDDs can be exponentially smaller than OBDDs. All right, so that's the big reward, that for some Boolean functions or knowledge bases, this will blow up for any variable order, but this can be represented compactly, and that's the main win in this particular case. We talked in the past about how you can provide guarantees in terms of things like path width and tree width. We did not talk about this in detail, but let me just say, one of the well-known guarantees about OBDDs is that you can construct them exponential only in something known as path width. SDDs, you can give a guarantee in terms of something called tree width, and tree width dominates path width, so it's always less than or equal to that. So that's another way of looking at an advantage that one gets. But this is the key thing here, is that they are exponentially separated, and SDDs can be exponentially more succinct than OBDDs. Later, I'll give you a pointer to an open source SDD package that was released by my group. And now let's dig into the details and let's see what's going on with these folks. And to really give you the secret behind SDDs, we need to look a little bit about what really underlies these different circuit types that we looked at. So if you look at decomposability, that was a property that gave rise to DNNF circuits and structured DNNF circuits. So what you can see here is that we had a Boolean formula and we wrote it like this. We said, try to write it as a disjunction of conjunctions with the requirement that these G1 and H1 do not share variables, right? So every Boolean formula can always be written like this. The question is how many disjuncts you end up having. And if you recursively decompose each one of G1, H1 in the same way, you get basically DNNF circuits. And then we had a stronger version of decomposability called structured decomposability, where we said, yes, G1 and H1 should not share variables, but I want you to partition the variables in the same way across each disjunct. So you can see here A, C, B, D, the same. So this is really the basis of DNNF circuits and structured DNNF circuits. It's these formulas, is how can I take a Boolean formula like this and go ahead and decompose it or rewrite it in the following fashion. And as we've seen, if you're able to do this, then you can do SAT in linear time. And let's see now the next property we talked about, which is determinism. Now, determinism, we went ahead and added one more property, and we said we want these disjunct to be mutually exclusive, right? So I wanted F1 and F2 to be false, F1 and F3 to be false, 2 and 3 to be false. So this is decomposable, right? Because if you look, I rewrote F in these terms, and I made sure that G1 and H1 do not share variables. And then on top of that, I'm requiring that these disjuncts to be mutually exclusive. And then I got basically deterministic DNNF and then structured DNNF, all right? So everything rests on one step, which is known as how do you decompose the Boolean function. And one type of decomposition we've seen here gives you these circuit types, and you add another property on that decomposition and you get more circuit types. And then you can do more things. And remember, when we're doing Boolean function decomposition, we stop at this stage. I take the function and decompose it into these components. When you want to build a circuit, you have to repeat the process. So you have to take each of G1, H1, G2, H2, G3, H3, and then repeat the same process. So now we will look at what additional properties we put on such a decomposition to give us SDD circuits, all right? And you'll see it's just one extra step. Sometimes we refer at this as a strengthening of the property of determinism. So we're going to insist on determinism, but we're going to do it in a stronger way. So let's see how this works. So the fundamental idea behind SDDs is this notion of XY partition. What does that mean? So you give me the Boolean formula, and I'm going to partition its variables into X and Y, just like what we do in structured decomposition. And then I'm going to write it like this, all right? So what happened here? I took the variables of the formula and pretended they are into two disjoint sets, X and Y, and rewrote it like that. So far, what is this? This is structured decomposability, because G1 and H1 do not share variables. X and Y do not overlap, and I'm doing throughout, all right? So we have a structured decomposable rewrite if you want. Now, if you remember what determinism said that I want each one of these guys, like this guy and every other one, to be mutually exclusive. We're going to have that, but we're going to do it in a more or stronger way. I'm going to insist that these G's, G1, G2, G3, and so on, to be mutually exclusive and exhaustive. Now, the fact that they're mutually exclusive, if you take any pair of them and they are equal to false, that already gives you determinism, right? Because then every element like this or that will be conflicting the minute I have this. But I'm not gonna stop there. I'm gonna also want these to be exhaustive, and actually none of them can be true, it can be false. That's the requirement. And when I have something like this, I will say I have an XY partition of the Boolean function f, okay? And that is gonna be the basis of SDDs. So if you take your Boolean formula and decompose it in this particular way, that gives birth to a new circuit type with all kind of interesting properties. And those are what we called pictorially before the primes and subs. So when I do this, I'm going to call these primes and these subs. Now, when I looked at this from this angle only, if I rewrote it this way, in a way, there is no distinction between G1 and H1, right? They're basically symmetric in a way. But once I start putting these conditions, then there is a difference between the G's and the H's, right? The G's are what we call the primes, and the H's is what we're calling the subs. So you can think of this type of Boolean function decomposition, that is the XY partition, as rewriting it that way, and then insisting that the G's, which we call the primes, to be mutually exclusive, exhaustive, and they cannot be false. That is basically the Boolean function decomposition that underlies SDDs. Okay, let's take a concrete example, and will help us visualize this more. And before I do that, let me mention that sometimes we use this notation, which is more compact than that. So I will tell you, here's the XY partition for the function f. And the idea here is these G's are the primes, and they're over the variables x, and these H's are the subs, and they are over the variables y. And remember, the requirement is that if you take this and this, plus this and this, plus this and this, you get back f. And moreover, the G's should be mutually exclusive and exhaustive and not equal to false. That is what we call a partition. All right, so let's look at a concrete example. So here's a concrete example. This is my function f, and it is over 4 variables, a, b, c, and d. And I'm constructing an XY partition where this is x and this is y. Okay, so I put AB in one set and I put CD in another set. And that is an XY partition in this particular case. Let's see. First of all, I have 3 primes, AB, another prime, not A and B, and this is the third prime, B prime. Now, if you look at these 3 guys, they are mutually exclusive and exhaustive. If you pick any pair, they're not compatible with each other. And if you take the disjunction of all of them, that is, if you take A and B, or A prime and B, or B prime, that will end up being equals to true, right? So they're exhaustive. And if you pick up any pair, this and that, they conflict with each other. This and that, they conflict. This and that, they conflict. And none of them is false. Okay, again, this is what we call a partition. So if you look at this, this, and that, we call that a partition, mutually exclusive and exhaustive, and none of them is false. And you can see that this is deterministic. So if you took, let's call this guy here F1, and let's call this guy here F2, and let's call this guy F3, you can pick any of these pairs. F1 and F2 are conflicting with each other. F1 and F3 are conflicting. F2 and F3 are conflicting. So it is actually deterministic. But this is kind of a stronger version of determinism because the conflict is really happening on the G's, right? We need to talk about one more property here, which is all we need as far as the theory behind SDDs. And this is the notion of compression, okay? So I will say that an XY partition is compressed if it doesn't have equal subs. What does that mean? Here's a function. I picked up X and Y. This is how I partition its variables. And we came up with this XY partition, all right? So it has n subs and n primes. Now, if no two subs can be equal. So this is one sub hi and this is another sub ha. If they're not equal for all possible I and j, then I will say it's compressed. And here's the surprise. And the reason why SDDs end up being canonical is that if you give me a function and you partition its variables into xy, and therefore you're computing an xy partition, there is a unique compressed xy partition, right? Once more, here's a Boolean function. I split its variables into x and y, and I said construct an xy partition. There are many of them, but if I insist on that being compressed, that there are no equal subs, you can only do it in one way. And you will see how this ends up being the basis of why SDDs are canonical. But let's take actually a concrete example. This next example will not only illustrate what compression is, but it will also show you a systematic way for constructing XY partition. Remember what I'm going to do next because it's pretty important. Okay. Here's the function f over 4 variables, and I decided to partition its variables in this particular way. Now, I'm going to show you a technique for systematically constructing XY partitions and then guaranteeing that I'm going to get a compressed one. So the idea is pretty simple. The idea is you take the variables over which I'm going to construct the primes, and you look for, and you list every possible instantiation of them. Now, this is not efficient. This is for theoretical reasons and could be useful for small problems. Like if you're solving small problems, it's very convenient. So 2 variables, A, B, and there are 4 possible instantiations of them. And I'm going to use these as my primes, okay? That works because these are mutually exclusive and exhaustive, and none of them is false, all right? Now I want to construct the subs. So what do? For every one of these primes, I'm going to go and condition that formula on that. So this is like saying A is true and B is true. Let me fix A true and B true in that and see what does the formula reduce to. Help me out here. What ends up being the formula when I fix A to true and B to true? What does this reduce to? And someone is saying true. Fantastic. That would be the sub here. Now, let's do the second guy. If A is true and B is false, what does this simplify to? I want to put something here. Someone is saying C, someone is saying C and D. Well, let's see what happens here. Here's the answer. So it's actually C and D. So if you take this formula and fix A to true, B to true, it reduces to true, that formula. If you fix A to true and B to false, it simplifies to this. If you fix A to false and B to true, it simplifies to that. And finally, for that last guy, I get this. Now, here's something, guys. I already have an XY partition, and that is this and that, or this and that, or this and that, and so on, okay? 4 primes, 4 subs. Once more, why is this an XY partition? Because these guys are mutually exclusive and exhaustive, and none of them is false, so they represent a partition. So I'm good, okay? So this is a very simple method that allows you to always construct an XY partition for a particular Boolean formula. The question I have for you now is this a compressed partition? Is this a compressed XY partition? And people are saying no. And why? What is the violation here? Remember, if you have equal subs, it's not compressed. And fantastic. Someone's saying that the second sub and the 4th sub are equal, and that makes it not compressed. So what do? You can always compress. It's pretty simple, right? Anytime you have equal subs like these, I can get rid of them. How? Can someone suggest, merge them? How do I merge them? How do I merge them? I have this and that, or this and that, and I want to make it only this and that. And okay, someone is saying, or the primes. Fantastic. People are stating this in different ways. Someone is saying, or the primes. Someone is saying, resolve over A. They're all correct, and that's what ends up happening. So I'm going to put this here, and then I take this prime and that prime and disjoin them. So I'm doing A and B prime or A prime and B prime, which happens to be equal to B prime. And that's what I put here. So I just disjoined the primes. Now, in this case, I had only one violation. There were only two equal subs. If there were three of equal subs, three primes that have the same sub, I just take the disjunction of the three primes. And if I had more violations, I can do the same. And you can see how this process is going to yield a unique output, right? And this now is compressed. Okay, so this is a very important technique. You guys need to remember this because it could be the secret for answering a whole bunch of questions. Once more, a systematic way for constructing an XY partition is to consider every possible instantiation of the X variables and take these as your primes. Now you're going to get an exponential number of primes in this case, exponential in the number of variables X, but that's fine. And that immediately gives you XY partition, but it may not be compressed, and you can see how you can compress it. And now you'll see why SDDs are canonical, because armed with this result that I can always have a unique compressed XY partition, let's see how you can construct conceptually SDDs based on this result and why the result will end up being canonical. Okay, here's the fun part. Now that we have the ingredients that we want, let's look at this Boolean function. And let's see how we can construct an SDD for it. All right? Now, remember what we said. You need a Vtree. An SDD is based on a Vtree. What is the Vtree? The Vtree is just a binary tree. Pick any one you want. The only requirement is the leaves of that Vtree have to be your variables, to be in one-to-one correspondence with your variables. Now, let's see. What role does this Vtree have? Okay, guys, this is pretty fun here. Here's the Vtree. And the idea is every node in the Vtree is dividing your variables into X and Y. So the very root, okay, the numbers 6 to 5 are arbitrary here. There was also numbering for the leaves and I removed them, but ignore that. Just labeling of these nodes. Now, look at the root. What does the root say? It says, when you start representing this as an SDD, first compute an XY partition where X is the variables in the left subtree and Y are the variables in the right subtree. So, because anytime you want to construct an XY partition, you need to know what X is and what Y is, and that's telling me. Now, I'm going to go construct an XY partition based on that, and I want it to be compressed. Now, we've seen that already on the previous slide for this example, and here's how it looks. I have 3 elements, 3 primes, and 3 subs. Okay, so what does that mean? That means I already know how to draw my first decision node for the SDD, right? All what this is doing is basically representing that particular guy. Now, what I need to do at this particular point is to take these guys and similarly represent them as SDD. And if I take this guy, now I need to know how to partition it. So I need an X and Y, and that's where this left subtree is doing. So this is saying partition X into this, X and Y into that. And if I want to do this, similarly, I do it according to that. And if I want to convert this into an SDD, I use this for that. Okay, so you see what's going on here is that as I take this guy and decompose it using XY partitions, every time I need to know what X is and what Y is. That's all I need, because once I know what X is and Y is, I'm done. There's only one way to decompose. And the Vtree is giving you a recipe for doing this. It says start here, do X and Y. You're gonna get formulas over this X and formulas over that Y. When you wanna decompose them again, I'm telling you how, left and right and so on, okay? And that's what we basically were getting in this particular case. So the first decomposition, first decision node, that leads to these guys, all right? Remember, this is on the left, this is on the right. And to decompose each one of these, you know which choices of X and Y. So let's do the first one. This guy, that's my X, that's my Y. There's only one compressed XY partition in this case, and it happens to be this guy. All right, we didn't do this one, but you can try it at home, that the only way to generate an XY partition for this compressed using this X and that Y is this. What does that mean? That means now, if I go back to this, that means I can replace this with a decision node, and it ends up being like this. You do it for the other guys, and that's your full SDD in this particular case. You keep repeating this process until you reach boundary cases. Boundary cases are true and false, or literals, and that's it. All right. The two fundamental concepts here is one, the notion of a compressed XY partition, and the second fundamental concept is the Vtree, which tells you which XY partitions to construct at every step. And what you realize when the SDD is constructed, every decision node corresponds to some Vtree node. Why? Because that node corresponds to an XY partition where X is the left variables and this is the Y variables, all right? So if we go back to this animation here, the root node is not, we say, normalized for that. Why? Because this corresponds to an XY partition where this is X and that is Y. And this other guy here is normalized for this because it's an XY partition where this is X and this is Y. And similarly for the other guys. So there is this notion of an SDD node or an SDD decision node being normalized for a Vtree node, and I hope that's clear by now. Now, people are saying, why are the numbers 6 to 5? That's arbitrary. This was, what was it? It was 0, 1, 2, 3, 4, 5, 6. So this was a particular numbering of the nodes, and I deleted those numbers, so these looks arbitrary. It's just an arbitrary labeling of the Vtree nodes. This is generated automatically by the SDD package. Let's see. What else do we need to say here before we move on? I need to say two things about the relation with OBDDs, because we've seen at a superficial level how OBDDs are a special case, but let's see it now more concretely. What happens is if you always construct XY partitions that look like this, where on this there's only a single variable and all other variables are in Y, what happens to the XY partition? It looks like this. Remember, two primes, X and X prime, the possible instantiations of that guy. And then what are the subs? The subs are F given X and F given not X. This we know. This is called the Shannon decomposition. So the Shannon decomposition is a special case of XY partitions. The Shannon decomposition always says split the variables into one variables and the rest. XY partitions say, no, you can split the variables into any two sets. And if you always do them this way, you get Shannon decomposition as a special case of XY partition. And let's look at it from the Vtree point of view. Remember the right linear Vtree. We said if you use a right linear Vtree, then you get an OBDD. Why? Look at it. I'm starting by splitting on, initially starting with this root node. It says split your variables into X and everything else, correct? So that gives you a Shannon decomposition. And after that, it says, you know, if you're here, split it into B and everything else. So if you do that, you're always going to have XY partitions that have only two elements in them, and the primes are basically literals. So if you construct an SDD like we talked using this Vtree, it looks like this, which is nothing but an OBDD. You see that, guys? Very nice. It is remarkable that this was only discovered 10 years ago, even though OBDDs have been for decades, and people have been trying actually to generalize them for a very long time. And the breakthrough was this notion of XY decomposition. So this is in a paper I wrote in 2011 in HKI. Initially, the notation for SDDs were this, and what we've seen on the previous slide, which is this guy here. In more recent papers, we started adopting more like the circuit notation people use in engineering. And this is actually an SDD. And if you look at it carefully, you'll see that it's made up of fragments that look like this. Let me mention this because actually it's interesting. We draw some connection to digital logic. This is the OR node, and these are the elements. And if you basically label these, you can see that these are the primes, G1, G2, G3, and these are the subs. Now, what did we say about the primes for OBDD, for SDDs? Mutually exclusive and exhaustive. What does that mean on circuits? That means regardless of what circuit input you apply, precisely one of these guys will be high and the other two will be low. In this case, high is red, low is blue. And in this case, you can see that this is high and these two guys are low. What does that mean? That means this fragment is passing this signal through and suppressing these two signals, right? A decision, I'm making a decision, which one of these signals to pass through. In this case, it's gonna be this guy. Why? Because this is the guy that is high. Doesn't matter what input you apply to the circuit, precisely one of these will be high and the other two will be low. And that means that we're passing the corresponding signal. And you can see why this OR node will be deterministic. Because if the two guys that are inactive will generate a low signal, and the guy that's active, that's the only guy that will generate a signal that could be either low or high. So because of this, this OR gate will never have more than one high input, either no high inputs at all or just one. And therefore it's deterministic. So this is a more restricted type of determinism, okay? And that's what we have as SDD circuits. And of course, they are basically structured according to a Vtree. So if you look at decomposability and determinism, what happened here for SDDs is that we are using decomposability and determinism, but stronger version of each. So we're using structured decomposability and we're using partition determinism. We strengthened each one of them, and that gave rise to SDD circuits. And because they have stronger properties, they also give you more. And we'll see later, there's a lot of applications of these indeed, particularly in probabilistic reasoning and in learning from data and knowledge, a very nice and powerful tool. I just want to say one more thing before we get to our break. And that is, how do you combine these? What does the apply operation for these look like? Because we mentioned that these guys have an apply operation. And given what you know about OBDDs and how we implement apply there, I just have to show you one result, and everything else is carried from how we do OBDDs. And the main idea is, if you give me an XY partition of a function f, and it looks like this, and another XY partition of a function g, and it looks like this, and you ask me, how do you get an XY partition for a Boolean combination of these guys? So this circ could be either conjunction or disjunction or some other Boolean operator. And it turns out you can do it this way. What is this saying? Say, take every possible combination of a prime for f and a prime for g. So pick any p and any r. Look at all combinations. So I have n of these and m of these. So in principle, I have n by m possibilities. These would be the primes for that guy, as long as their conjunction is not false. So pick a pair, a prime from here and a prime from there. If they're not false, that's a prime for the result. And the sub will be simply the corresponding sub of this guy and the sub of that guy circed. Okay, so you can see that this is at most m by n, the size of this. Effectively taking the Cartesian product of these two guys and throwing away the members that have basically incompatible primes. And the observation is, this is a simple way to actually construct an XY partition for this from the XY partition for this and that. That ends up being the basis of the apply operation. And the rest is very similar to the OBDD, and you have to cache and da. The one caveat here is that this apply, as I described it, can be implemented and will be quadratic like OBDDs, except the resulting OBDD is not, or SDD is not guaranteed to be compressed. Okay, and that is not easy to ensure. So the difference here between this and OBDDs is, yes, we do have an apply operation and it's quadratic, but it doesn't guarantee that the result is actually compressed, but it will give you an SDD in quadratic time, and that's the basis of the apply operation. And next we'll see how we're going to use it actually, or can be used to do bottom-up compilation. So we're now at our break time, and that's actually a good point because we're going to start another segment when we get back. So let's take our 10-minute break, and when we come back, we will talk about bottom-up compilation of both OBDDs and SDDs. Thank you.